mathematics. How much gold can you hold in an elephant's ear? When it's noon on the moon, then what time is it here? If you could count for a year, would you get to infinity or somewhere in that vicinity? When you choose how much postage to use, when you know what's the chance it will snow, when you bet and you end up in debt. Oh, try as you may, you just can't get away from mathematics.
Hey, grade 12 class, special video for you coming to you in the afternoon on Wednesday, April the 15th. Just a little video to go over two of the questions that have been asked the most often off of the review exercise. This will give you a chance to check out these two solutions and to be able to finish up that assignment today so that tomorrow when I give you the new assignment on the last topic in this unit, we'll be able to go and get that done quickly. So question 78 was probably the most asked question. And question 78 is a fun question. I like this kind of question because it brings in together a couple of units. So it brings in sort of all your physics knowledge that you have. So you've got the question in front of you, but I'm going to read it anyway. It says a human cannonball has a spring constant of 35,000 newtons per meter. The spring can be extended up to 4.5 meters. How far horizontally would a 65 kilogram clown be fired if the cannon is pointed upward 45 degrees to the horizontal? So I've drawn my diagram here. I've got my cannon, I've got my clown in the cannon, the spring is compressed with the clown against it. The clown's going to get shot out of the cannon. So we're going to split this up. The first thing we have to do is figure that this is a projectile motion question in essence, right? It's going to get projected out, it's going to go up, it's going to follow this parabolic shape, and it's going to hit the ground somewhere over here, and it is this dh that we need to find. Well, in order to solve that, the first thing we need to do is figure out with what velocity is he leaving the cannon. What is the velocity that this projectile is being fired at? So to do that, we're going to look at energy. Because at point A here, when the clown is in the cannon, the spring is compressed, this clown has elastic potential energy. As he gets shot out of the cannon, at B here, there's no more elastic energy, but he's got kinetic energy. So if we look at our conservation of energy, we say that the total amount of energy at A has to equal the total amount of energy at B. Right, that's the law of conservation of energy. That means that the elastic energy at A has to equal the kinetic energy at B. Again, at A, he has no kinetic energy. He's at rest up against a compressed spring. Okay, so there's only elastic potential energy. At B, the spring is no longer compressed, so there's no elastic energy. All that elastic energy that he had at A has been transferred into kinetic energy. All right, so that means EE at A has to equal EK at B. Half kx squared equals a half mv squared. The halves will cancel out, right? Multiply both sides by 2, halves are gone. 35,000 times 4.5 squared has to equal 65 kilograms times the velocity squared. Solve for velocity and you get 104.4 meters per second. That is the velocity that the cannonball, or the clown in this case, has at B. It's the velocity this projectile is being shot with. Now, the energy part of this question is done. We are now moving into a projectile motion question. So here's where you might have to go back in your notes and look at projectile motion questions. When we did projectile motion questions, the first thing we always did is if we were given a velocity on an angle, we needed to find the horizontal velocity and the vertical velocity. So I've done that calculation over here. The horizontal velocity, which is the adjacent side of a right triangle, the cosine of the angle, cosine of 45, times the velocity of the hypotenuse of 104.4 gives us 73.8. The vertical velocity is going to be the same. It's the sine of 45 times 104.4, also 73.8. And of course, you know that because you're amazing calculus, pre-calculus students who know that the cosine of 45 and the sine of 45 are the same number. All right, so now once we have our vertical and horizontal velocities, we're going to split this question into two pieces, two parts. We're going to look at it vertically and we're going to look at it horizontally. we're going to look at it vertically to find the time, and then we'll use the time to find the horizontal distance that this clown travels. So, looking at it vertically, we have initial velocity of 73.8 meters per second. At the highest point, vertically, the clown will stop rising. So at the highest point, you'll have a V2 equal to 0. And of course, vertically, this clown will be decelerating at negative 9.8 meters per second squared, or 9.8 meters per second squared down. All right, using one of our kinematics formulas, okay, the acceleration formula, change in velocity over time, rearrange it to solve for time. We get V2 minus V1 over A. Plug in our numbers. That will give us a time of 7.5 seconds. Now again, this is the time from the beginning to the highest point. Okay, we're going to multiply that by 2 to go from the highest point back down to the ground. So that gives us this whole parabola now. So 7.5 times 2 is 15 seconds. This clown will be in the air for 15 seconds. All right, now we have the time. Again, time is the one quantity that transfers from vertical to horizontal, right? The time in the air vertically is the same as the time in the air horizontally. So we'll bring that time into our horizontal section. Horizontally, we have a velocity, and remember that horizontally in a projectile motion question, the horizontal velocity remains constant. There's no acceleration, no deceleration. It's a constant velocity. We have a time of 15 seconds. Our formula, d equals velocity times time. Plug our numbers in, and you'll get 1,111.5 meters, or if we round that to significant digits, it's 1.1 times 10 to the 3 meters, and that is how far this clown will go, which is a fairly significant distance that this clown's going to be traveling. So that's how you do that question. Again, if this didn't make sense to you, send me an email and we'll go from there. Let's go into the other question. Question 85 was the other question that I was asked a lot of, and we're going to do that on the other board. Here is question 85. Now, I've done this question a couple of different times in a couple of different ways, because you can always do questions more than one way, and I get the same answer every time, which is not the same answer that's on the paper that I gave you. It's close, it's in the ballpark, but it's not quite the same. So I believe that possibly there's a typo on the paper. If I've made a mistake here, if you see that I've made a mistake here, let me know, and we can correct it. But I keep getting the same answer in multiple ways that I've done it. So here's the situation. We have a spring with a block up against it, a 3 kilogram block. The 3 kilogram block has compressed the spring 12 centimeters, 0.12 meters. Okay? Spring then gets released and the block is moving out. The question asks us to find the speed of the block, the velocity of the block, when the spring has been released 10 centimeters. So that means the spring is still compressed by 2 centimeters. So it was originally compressed by 12 centimeters. We're looking at it when it is compressed 2 centimeters. Okay? So again, we're going to look at conservation of energy. When this block is sitting up against the spring, compressed at 12 centimeters, at A, here we'll call that point A, it only has elastic energy. It's at rest, and it's up against a compressed spring, so it has potential energy, elastic potential energy. Spring gets released, the block starts moving. That elastic energy starts getting transferred into kinetic energy, and at point B here, where the spring is still compressed by 2 centimeters, it has a little bit of elastic potential energy still, but the valid block is moving, so it also has kinetic energy. So again, we're going to go E total A equals E total B. At A, as we said, it only has elastic potential energy, but at B, it has both kinetic energy, because now the block's moving, and a little bit of elastic potential energy, because the spring is still compressed. Fill in our formulas, a half kx squared for the elastic energy, a half mv squared for the kinetic energy, another half kx squared for the elastic energy at the new compression. Multiply everything by 2, the halves disappear again. Fill in our numbers. The spring constant was 350 newtons per meter, compressed 0.12 meters squared, 3 kilogram block, the velocity squared, our spring constant 350 times 0.02 meters squared. Solve for V and we get 1.3 meters per second. I believe the answer in the textbook was 1.1, or on the sheet was 1.1. Again, if you get 1.3 or somewhere in that ballpark, I think exactly it's like 1.27 or 1.28, somewhere in that range, we'll consider it as the right answer. And again, if you find that I've made a mistake here, let me know. But again, I've done this a couple of different times and gotten this answer each time. And but I mean, it's possible that I made a mistake. If you find that, let me know. But if you did your work this way and got this answer, I'm going to consider it right, and we'll move on from there. Tomorrow, we'll have a lesson on elastic collisions, and we'll finish up this unit with that lesson. Have a great day, and we'll see you tomorrow.